Greetings of the day to all of you. In today's lecture, I am going to draw a comparison between two shunt compensators. One is thyristor-based shunt compensator, which is also called static wire compensator, SVC. And another shunt compensator is converter-based shunt compensator, which is also called static synchronous compensator, STATCOM. So SVC is a thyristor-based shunt compensator, and STATCOM is a converter-based shunt compensator. Both types of shunt compensators more or less perform the same tasks. Then what is the difference between the two? Apart from topological, differences, what are the characteristic differences or performance differences between the two, and which one you will choose? For example, tomorrow if as an engineer you have to make a choice between the two shunt compensators, what are the various factors which you should consider while making a choice between the two shunt compensators, that's between SVC and STATCOM? For that purpose, it is very important to understand to draw a comparison between the two types of shunt compensators. So that we are going to do in today's lecture. In today's lecture, we are going to draw a comparison between static wire compensator, that's SVC, and static synchronous compensator, STATCOM. Comparison between SVC and STATCOM. So this is what we are going to study today. So the first point of comparison between the two shunt compensators is if you consider voltage versus current characteristics and voltage versus reactive power characteristics. VI and VQ characteristics. Let us first of all take STATCOM and draw VI and VQ characteristics for STATCOM. Then we will draw the VI and VQ characteristics of SVC, and we will make a comparison between the two, and we will try to see which one is better as far as VI and VQ characteristics are concerned. Let me first of all draw the VI and VQ characteristics for STATCOM. So first of all, I am drawing VI characteristics on this graph. This is inductive current IL. Along this axis we have inductive current. That means STATCOM is operating in inductive region, and along this axis it is operating in capacitive region, IC. So this is inductive region of operation for STATCOM. I will write here inductive along this axis, and along this direction the same STATCOM is operating in the capacitive mode. Okay, and this is the bus voltage VT, and let us take this in per unit. So the various characteristics are like this. This is 1.0 per unit. This is 0.9 per unit. This is 0.8 per unit, 0.7, 0.6, 0.5, 0.4, 0.3, and 0.2. Fine. So this is maximum inductive current. Here I should write IL max, and along this axis, negative x-axis, this is the maximum capacitive current drawn by STATCOM, IC max. Okay, now this is 1 per unit. Here the terminal voltage or the bus voltage is 1 per unit. Then it drops to 0.9 per unit, 0.8, 0.7, 0.6, 0.5, 0.4, 0.3, and 0.2. Right. So I have already told you in one of the earlier classes, maybe last class when we were discussing the VI characteristics of a STATCOM, that STATCOM has some transient rating, which is a sort of overload rating. Okay, so this is transient rating of STATCOM, transient rating, and that means the STATCOM current can go more than IL max in the inductive region. for a very small period of time, t less than 1 second. This is called transient rating. Similarly, in the capacitive region also, it has got some transient rating. So this is transient rating. I should show here, I should write here transient rating. That means in the capacitive region of operation, the STATCOM can draw capacitive current slightly more than IC max for a very small period of time, t less than 1 second. Fine. So this is VI characteristic of a STATCOM, and it is very interesting to see that first of all, let me tell you why I have taken a slightly positive slope. You know, this characteristic is not exactly a straight line, it is slightly having positive slope. All these characteristics are having a very small positive slope, and this positive slope is deliberately accommodated in the VI characteristics of a STATCOM, because it is helpful for the parallel operation of various STATCOMs. For example, instead of using one STATCOM, if you use number of STATCOMs in parallel, then parallel operation will be facilitated. It will be made easy if all the STATCOMs have VI characteristics with a slightly positive slope. So slope is slightly positive. Now, these VI characteristics of STATCOM we have already studied in one of the earlier classes, probably last lecture, and I have told you that the main characteristic of a STATCOM is that it draws the current, which may be inductive current or capacitive current, depending upon whether it is operating in the inductive region as inductor or in the capacitive region as capacitor. That means whether it is absorbing the reactive power or generating the reactive power, the current is independent of the voltage. For example, what is the maximum current? This is maximum inductive current, and it's at a bus voltage of 1 per unit. You can see bus voltage, if it drops from 1 per unit to 0.9 per unit, what happens to the current? It still remains IL max. Similarly, as the voltage goes on decreasing from 0.9 to 0.8, 0.7, 0.6, 0.5, 0.4, 0.3, 0.2 and so on, the current does not change, current remains same. Similarly, if you assume that the STATCOM is operating in the capacitive region, capacitive mode, and it is drawing maximum capacitive current, IC max, at a bus voltage of 1 per unit. And you can see as the bus voltage decreases, the current does not decrease, current remains constant. Say for example here, bus voltage is 0.3 per unit, but what about current? Current is same, it is still IC max. So therefore, the current, reactive current, which may be either inductive current or capacitive current drawn by a STATCOM, is independent of the bus voltage. Okay. Now, let me now on this side draw, this is about VI characteristic of STATCOM. What about VQ characteristic? I can very easily now draw the VQ characteristic of a STATCOM. Now this is reactive power, inductive reactive power, QL, and this is capacitive reactive power, QC. Again, this is the inductive region of operation. If the STATCOM is drawing inductive current, that means it is operating as an inductor, it is absorbing the reactive power. So it is operating in the inductive region or inductive mode. On the other hand, if the STATCOM is drawing leading power factor current, capacitive current, that means it is operating in the capacitive region and it is generating the reactive power. It's not absorbing the reactive power, it is generating the reactive power. So this is capacitive mode of operation, and this is terminal voltage or bus voltage, again in per unit. Now we know that the reactive power drawn by a STATCOM is the product of voltage and current. Okay, and since current is independent of the voltage, you can see here current from this VI characteristic, the current drawn by a STATCOM is independent of the voltage, it remains constant. So that means a reactive power drawn by a STATCOM is directly proportional to voltage, because current is constant, I is constant, it is independent of the voltage. So it is, let me call this voltage as Vt, so Q is directly proportional to Vt. Okay, so this gives us an idea about what these QV characteristics or VQ characteristics should look like. So let me again start from here. This is the bus voltage 1 per unit, and let us assume that This is the maximum in the inductive mode of operation. This is the maximum inductive reactive power drawn by or absorbed by STATCOM. And in the capacitive mode of operation, let us assume this is the maximum capacitive reactive power QC max generated by STATCOM. Okay, and this is at a full voltage, rated voltage 1 per unit. And this equation tells us that as the terminal voltage decreases, the reactive power linearly changes with terminal voltage. If terminal voltage decreases by 10%, the reactive power drawn by STATCOM also decreases by 10%. So it has a linear relationship like this. So you can show it like this. In the inductive region, and this is for the capacitive region. Okay, so let me first of all complete these characteristics. And this is transient rating. Again, this is transient rating, and here also you can consider this as the transient rating. Fine. Now this is 1 per unit. This is 0.9 per unit. Okay, this is 0.8, 0.7, 0.6, 0.5, 0.4, 0.3, 0.2 per unit. Now let us assume that the STATCOM is operating in the inductive region and it is absorbing the reactive power, and let us assume it is absorbing the maximum reactive power QL max at rated voltage. Then when the voltage, the bus voltage decreases from 1 per unit to 9 per unit, 1 per unit to 0.9 per unit, the reactive power will also decrease by the same percentage. Okay, so for example here the terminal bus voltage is decreasing by 10%. So the reactive power will also decrease by 10%. It will not remain constant now. At a bus voltage of 1 per unit, the reactive power absorbed by STATCOM is QL max, maximum. And when voltage drops from 1 per unit to 0.9 per unit, how much reactive power is it now absorbing? It is absorbing this much of reactive power, which is less than QL max. And when voltage drops from 0.9 per unit to 0.8 per unit, it is drawing less reactive power. Similarly, 0.6, 0.5, 0.4, 0.3, for example, at 0.3 per unit, this bus voltage, it is absorbing only this much of reactive power, and so on. Same is the case when it is operating, when it is generating the reactive power, it is operating in the capacitive region. At 1 per unit, 100% or rated voltage, it is generating maximum capacitive reactive power QC max, and as the voltage decreases, the reactive power generated linearly decreases. For example, at a bus voltage of 0.6 per unit, it is generating this much of reactive power. So therefore this graph tells us, we have got this graph from this equation. So reactive power is equal to Vt into I. I is constant. From these characteristics, the current drawn by a STATCOM is constant. It is independent of the bus voltage. So therefore Q is directly proportional to Vt, and as Vt decreases, the bus voltage decreases in both regions, the reactive power absorbed or reactive power generated by a STATCOM linearly decreases. It linearly varies with the bus voltage. Okay, that's about STATCOM. What about this SVC? Let us quickly draw the same characteristics for SVC. Now I will write here SVC. For SVC, let me first of all draw VI characteristics. Again, this is this is inductive current and this is capacitive current. In this region, your SVC is operating in the inductive mode, and in this region, it is operating as a capacitor, that is capacitive mode. It is generating reactive power, and this is the bus voltage Vt in per unit. In case of SVC, the current drawn by SVC is not independent of the terminal voltage. It linearly varies with terminal voltage. The current drawn by an SVC, for example, just few moments back you have seen the current drawn by a STATCOM is independent of the voltage. It does not depend on the voltage. Whatever the bus voltage is, it remains constant. But in case of SVC, that's not the case. In case of SVC, the current is directly proportional to the bus voltage. As the bus voltage varies, current linearly varies. So that we can show like this. This is the current drawn by SVC at rated voltage 1.0 per unit, and then it varies linearly like this. Okay. This is IL max, and this is maximum capacitive current, IC max. The SVC has transient rating like this. This is transient rating. Okay, so you can see similarly in the capacitive region it may have some transient rating. This is 0.9 per unit. This is 1 per unit, 0.9 per unit, 0.8 per unit, 0.7 per unit, 0.6 per unit, 0.5 per unit, 0.4 per unit, 0.3 per unit, and 0.2 per unit. Now let us assume the SVC is operating at in the inductive region. It is absorbing the reactive power, okay, and it is operating at rated bus voltage 1 per unit, 100% voltage, and the current drawn by SVC is IL max. And as the voltage decreases from 1 per unit to 0.9 per unit, the current drawn by SVC also decreases linearly. Okay, it decreases from this value to this value. Similarly, as the voltage decreases from 0.8, 0.7, 0.6, 0.4, for example, at a voltage or bus voltage of 0.3 per unit, what is the inductive current? It is only this much. Same is the case with the capacitive, in the capacitive region. At a rated voltage, if the maximum capacitive current drawn by the SVC is IC max, then as the voltage decreases, the current drawn also linearly decreases. So therefore, current drawn by an SVC is not constant. It is not independent of the bus voltage. It varies linearly with the bus voltage as shown by these characteristics. So this will give us an idea about how a VQ characteristic should look like. Let us draw now VQ characteristic for an SVC. This is again bus voltage in per unit. This is QL, okay, and this is QC, right? This is inductive region of operation. When inductive power is QL, that means SVC is absorbing inductive power, it is operating in inductive region. And if it is QC, that means it is generating the reactive power, injecting that reactive power into the bus, it is operating in the capacitive region. And this is the terminal voltage or bus voltage at 1 per unit, for example. Okay. Now it is very interesting to see the reactive power is again equal to Vt into I. Since I is proportional to Vt, so therefore inductive power is proportional to Vt into, instead of I can write Vt, so it is Vt into Vt square. That means in case of SVC, the reactive power is not proportional to bus voltage, it's proportional to square of bus voltage. That means if the bus voltage decreases by 2%, the reactive power absorbed or generated will decrease by 2 raised power 2, that's 4%. So therefore, the Q is proportional to Vt square. So you will have this type of characteristic, parabolic characteristic, like this. So this will be the type of characteristic. This is maximum reactive power, inductive reactive power QL max, and this is maximum capacitive reactive power QC max. And it may have some, this rating also, transient rating also. For example, it may have this transient rating in the inductive region as well as in the capacitive region. This is transient rating. Now this is 1 per unit, this is 0.9 per unit bus voltage, this is 0.8 per unit, 0.7 per unit, 0.6 per unit, 0.5 per unit, 0.4 per unit, 0.3 per unit, and 0.2 per unit. Now we can see, let's assume that our SVC is operating at the rated bus voltage and it is absorbing the maximum reactive power QL max. Now as the voltage decreases from 1 to 0.9 per unit, how much reactive power it is drawing? It is drawing this much of reactive power. The reactive power drawn by it decreases by square of voltage, it's not proportional to VT, it's proportional to VT square. Similarly, at 0.8 per unit, it is drawing still less reactive power, and so on. Same is the case with when it is operating, when it is generating the reactive power, when it is operating in the capacitive region of operation. So therefore, if you compare the VQ characteristics of STATCOM with the VQ characteristics of this SVC, in case of STATCOM, the reactive power is directly proportional to voltage. But in case of SVC, the reactive power is directly proportional to square of voltage. So therefore, as the bus voltage decreases, in case of a STATCOM, the reactive power decreases linearly with bus voltage. But in case of SVC, the decrease in the reactive power decreases as square of the bus voltage. So therefore, there is more decrease in reactive power generated or absorbed by SVC with decrease in the bus voltage as compared to that of STATCOM. So because of this, we can say that STATCOM provides more effective compensation and voltage support under large voltage disturbances. Okay, so if there is a voltage disturbance, drop of the voltage, large drop of the voltage because of some fault, the voltage support provided by STATCOM is higher than the voltage support provided by SVC, because in case of STATCOM, when the voltage suddenly drops due to some fault, the reactive power exchanged by STATCOM drops, it's proportional to, it drops linearly with the bus voltage. But in case of SVC, it drops as square of the bus voltage. So the drop in the reactive power is more in SVC than drop in the voltage in case of STATCOM. So therefore, STATCOM provides much better and more effective compensation and more effective voltage support under large voltage disturbances. Hence, we can say that for same compensation, an SVC of higher rating is required. I will write this statement here. From these characteristics, we come to the conclusion that since STATCOM provides more effective compensation, so if the compensation required is same, for same compensation, an SVC of higher rating is required. Or in other words, a STATCOM of lower rating is required. So therefore, these characteristics prove that STATCOM provides better or more effective compensation than SVC, because STATCOM has a feature that it maintains the current constant, independent of the voltage, bus voltage, whereas the current linearly changes or decreases with bus voltage in case of SVC. So from these graphs, we have seen that STATCOM provides better compensation than SVC. So this is first point of comparison. So it goes in favor of STATCOM. Second is transient stability improvement. Transient stability improvement. Let us see which compensator provides better. Both are shunt compensators, and which compensator provides better stability, transient stability improvement. What is transient stability? We already know that transient stability is the ability of a system to recover after a major disturbance. The disturbance may be a severe three-phase fault which will result in step-like decrease in electrical power transmitted, and it will result in acceleration of the rotor or machine, and hence it may result in unstable operation. If the system recovers from this, then we say that the system has got transient stability, it is stable. Let us first of all see transient stability improvement provided by STATCOM. Okay, this is delta, that's transmission angle or power angle versus power. Okay, so this is, for example, uncompensated system. This is a uncompensated system. Uncompensated system for which P is equal to V square by X sine delta. You know, and this is the maximum P max equal to V square by X for uncompensated system. Now let us suppose that we connect the shunt compensator. So how do we connect shunt compensator? This is our shunt compensator. It is connected like this. This is the schematic diagram of a shunt compensator. It is connected with the system like this. This is sending end voltage equal to V at an angle of delta by 2. This is receiving end voltage VR equal to V at an angle of delta by 2. This is Jx by 2, transmission line reactance, half of the reactance here, half of the reactance here. This is I and this is IC. This is STATCOM, parallel operation of STATCOM with the transmission system. Now when the STATCOM is connected in the middle of the transmission line, it provides the reactive power compensation by providing the required reactive power. It provides the reactive power compensation, and the characteristics get modified like this. So this is our characteristic here. P is equal to V square, 2V square by X. We know that for shunt compensator it is 2V square by X sine delta by 2. Okay, and how much is the reactive power, or how much is the maximum power? It is 2P max, because it is 2V square by X at delta equal to pi, right? Then this is, let's say here capacitive current is IC max 1, here capacitive current is more, IC max 2, here capacitive current is still more, IC max 3. Okay, well, let us suppose that earlier our system was operating here where the electrical power transmitted was equal to mechanical input power, PM, and it was operating at a power angle or at a transmission angle of delta 1, and suddenly some major fault has occurred and transmission line is tripped. And the transmission line is tripped, the electrical power transmitted over the line is 0, but mechanical input power remains same. That causes acceleration of the machine, and as the machine accelerates, you can see as the machine accelerates, so delta increases. Let us suppose delta increases from delta 1 to delta 2. This is the increase in delta 2. And when the machine accelerates, the kinetic energy is absorbed by the rotating parts of the machine. Okay, so that's called accelerating kinetic energy, and that is represented by area A1. Area A1 represents the kinetic energy, accelerating kinetic energy. And as delta becomes equal to delta 2, let's assume fault is cleared and transmission line is reconnected. Okay, when the transmission line is reconnected, now your system it will not operate at delta 1, it will operate at delta 2, and at delta 2 the electrical power transmitted is higher. It is more than the mechanical input power. Mechanical input power is this much, but electrical output power is this much, so that will cause deceleration of the machine. So machine will start now releasing the stored kinetic energy, it will decelerate, and delta will keep on increasing. Delta will keep on increasing till at delta 3, the area A2, which represents the kinetic energy released by machine, or which represents the decelerating kinetic energy, A2 becomes exactly equal to A1. So A2 will be exactly equal to A1, and there is balance. Whatever kinetic energy was there stored, that kinetic energy is released, or accelerating kinetic energy becomes exactly equal to decelerating kinetic energy. If the system was operating, if the system was uncompensated, that how much was the area, this margin of stability? Only this much was the margin of stability for uncompensated system. But for compensated system with a capacitive current of, say for example, IC max 1, how much is the margin of stability? This whole thing is the margin of stability. Let us call this a margin. So this is the margin of stability. So therefore the STATCOM, which is a shunt compensator, it tremendously increases the or improves the stability margin of your transmission line or transmission system. So your system becomes more stable. So transient stability improvement is more. On the other hand, if we don't have, for example, if you don't use STATCOM as a shunt compensator, if you use SVC as a shunt compensator, SVC looks like this. This is again JX by 2, JX by 2, and this is sending end voltage, this is receiving end voltage, and SVC is, say for example, this is our SVC. It is connected across. This is a symbolic representation of SVC. Now, with this SVC, the transient, this is also a shunt compensator. It will also result in the transient stability improvement. And the transient stability improvement I can show on this side. This is delta versus P. Okay. Again, if you take this uncompensated transmission line, for uncompensated transmission line, this is pi, and this is again same P max, which is equal to V square by X, maximum power transmitted with uncompensated transmission line. And let us assume that the system operates here, and PE is equal to PM, electrical power transmitted over the transmission line, is equal to mechanical input power. Now as soon as SVC is connected, the transient stability improves. I mean, this characteristic, it goes up. For example, your curve becomes like this. This becomes your curve, and here IC is equal to IC max 1. Let us call this IC max 1, and P is equal to 2V square by X sine delta by 2, and this becomes 2P max. If more reactive power compensation is provided, then our capacitive current becomes IC max 2. If more is provided, then it becomes IC max 3, and so on. So this is the reactive power compensation. These are the this dotted line is power angle characteristic of uncompensated transmission system, and these are the modified power angle characteristics when reactive power compensation is provided by SVC, which is a shunt compensator. Now again, our system was earlier operating at delta 1, and fault has occurred, transmission line is tripped, electrical output has become 0, mechanical input remains same, and machine accelerates. And when the machine accelerates, let us suppose it accelerates from delta 1 to delta 2, and at delta 2 fault is cleared, and when the machine accelerates, this is the accelerating kinetic energy in the machine. And here fault is cleared, transmission line is reconnected in the system, and how much power, electrical power, is now transmitted? Not this much. More electrical power is transmitted over the line because the system is now operating at delta 2. So electrical transmitted power is more than mechanical input power, so machine starts decelerating. So it will keep on decelerating till your system operates, it reaches power angle or transmission angle delta 3, at which the decelerating area A2 exactly becomes equal to A1, and a balance is achieved. So whatever kinetic energy was stored, that is released, or accelerating kinetic energy A1 becomes equal to decelerating kinetic energy A2, and the system comes back to its normal operation, steady state operation. So how much is the margin of stability? Again, with uncompensated line, a margin of stability is very, very small. But with compensated transmission line, the margin of stability is more. So this whole thing is margin of stability, a margin, and it is much larger than the margin of stability provided by uncompensated transmission line. However, so therefore, whenever you use a shunt compensator, whether it is a STATCOM or SVC, okay, the margin of stability is improved. But you can very clearly see that the margin of stability is more, so you can say this area represents the margin of stability. It is more than the margin of stability provided by SVC. The margin of stability provided by STATCOM is more than margin of stability provided by SVC. It is because of the fact that since STATCOM maintains the reactive current or current constant independent of the voltage, so it provides better compensation. That's why the improvement in the transient stability is better in STATCOM than SVC. So it's clear from both are shunt compensators, both improve the transient stability of the system, but the improvement in transient stability by STATCOM is higher than improvement in transient stability by SVC. So therefore we can say that margin of stability, a margin provided by STATCOM is greater than the margin of stability provided by SVC. Okay, so therefore for same transient stability margin, I will write here, for same transient stability margin, if same transient stability margin is required, okay, a smaller rating STATCOM is required. A smaller rating STATCOM is required. So therefore, if you have to provide a certain margin of stability and you have to make a choice between SVC and STATCOM, since it provides better margin of stability, it improves transient stability of the system better than SVC. So therefore, for same margin of stability, making a comparison between the two shunt compensators between STATCOM and SVC, it's clear that the rating of STATCOM will be lower. A smaller rating STATCOM is required for providing same margin of stability. Okay, so therefore this point also goes in favor of STATCOM. Fine. Third is capability to exchange real power. Let me use a different color pen. Capability to exchange real power. I have told you that an SVC can exchange only reactive power, whereas STATCOM can exchange real power as well as reactive power. If proper energy storage is provided at the DC bus of a STATCOM, it can provide real power also. I told you that a STATCOM exchanges reactive power with the bus to which it is connected by voltage control, by modulation index control of STATCOM inverter. If modulation index of STATCOM inverter is increased, the STATCOM voltage becomes greater than bus voltage and it acts as a capacitor and it generates the reactive power and injects reactive power into the bus. If on the other hand the modulation index of STATCOM inverter is decreased, the inverter output voltage becomes less than bus voltage, it acts as an inductor and it absorbs the reactive power. Okay, but the voltages, the inverter, STATCOM inverter voltage and the bus voltage, they should be in phase. However, if I change the phase relationship between inverter output voltage, that's STATCOM inverter output voltage and bus voltage, I can make my STATCOM to exchange real power also, provided there is some energy storage like battery energy storage system or superconducting magnetic energy storage or supercapacitor or fuel cell at the DC bus of the STATCOM inverter. Then it can supply real power also. For example, how can it supply real power? If irrespective of whatever is the STATCOM output voltage, magnitude is not a concern, the phase angle is concerned. If STATCOM output voltage can be made to lead the bus voltage by an angle delta, which is also called power angle. So P is delivered. The real power is delivered to the AC bus. That means if you have an energy storage at the DC bus of STATCOM inverter, it will take that energy from the storage, convert that DC energy into AC energy and deliver that power or energy to the AC bus. On the other hand, if your controller makes STATCOM output voltage lag behind the bus voltage by angle delta, then P is taken or absorbed from AC bus. In that case, it does not supply active power to the AC bus. It draws active power from the AC bus, converts that AC active power into DC power, and that DC power is used for storage of the battery or storage of whatever energy storage you have there. Okay, so therefore the STATCOM has capability to exchange real power also if phase relationship between STATCOM inverter output voltage and bus voltage is changed. If V0 leads V, it delivers power to the AC bus. If V0 lags V, it absorbs or draws the power from the AC bus. Okay, so another very important feature of STATCOM is that it can independently exchange active and reactive power. STATCOM can independently exchange active power and reactive power with AC bus to which it is connected. Okay, the exchange of active power is independent of whatever reactive power is exchanged. Similarly, the reactive power exchange is independent of active power exchange. Another thing is that simultaneous active power and reactive power control can be achieved. Simultaneous P and Q exchange is also possible. So I have shown you that in one of the earlier classes previously. So with the help of this figure, so if your STATCOM is operating in first quadrant, then it supplies active power and it supplies reactive power also. When does it supply reactive power? It supplies reactive power if delta is positive. That means V0 is leading V, and it supplies reactive, this is Q, supplies Q, it supplies reactive power when STATCOM inverter output voltage is greater than the bus voltage, right? So if these are the conditions, delta is positive and V0 is greater than V, your STATCOM will supply active power as well as reactive power. You can make your STATCOM to absorb active power and supply reactive power if it operates in this quadrant. In this quadrant, it absorbs the active power and supplies reactive power. When does it absorb active power? When delta is negative. Negative delta means V0 is lagging behind V, and it supplies reactive power when V0 is greater than V. In the third quadrant, you can make your STATCOM absorb active power as well as reactive power. Absorbs active power as well as absorbs reactive power. When does it absorb active power? When delta is again negative. And when does it absorb reactive power? When V0 is less than V. And in the fourth quadrant, you can make your STATCOM supply active power and absorb reactive power. Supplies active power and absorbs reactive power. When does it supply active power? When delta is positive, means V0 leads V. And when does it absorb reactive power? When V0 is less than V. So if these are the conditions, like in the first case, delta is positive, V0 is greater than V. Your STATCOM simultaneously supplies active power as well as reactive power. But it supplies the active power provided it has energy storage at its DC bus available. And if your STATCOM can absorb active power, supply reactive power if delta is negative and V0 is greater than V. On the other hand, if delta is negative, V0 is less than V, your STATCOM can absorb active power, supply and absorb reactive power as well. And if your controller makes delta positive and V0 less than V, your STATCOM will simultaneously supply active power but absorb reactive power. So this gives 4-quadrant operation of STATCOM. So therefore STATCOM can exchange independently active power as well as reactive power, and various combinations are like this. And on the other hand, SVC can exchange only reactive power with the AC bus. it cannot exchange reactive power, whereas STATCOM has the capability to exchange real power also in addition to reactive power with AC bus. So this point also goes in favor of STATCOM. In fact, you can use STATCOM in such a situation where there is a fault, and in order to partially supply the power to the load to prevent the shutdown of the transmission system, the STATCOM take energy from the DC bus and supply energy or power to the AC bus, and partially some of the load can be supplied and shutdown can be prevented. Okay, so this point also goes in favor of STATCOM. Next point is physical size. Next point of comparison is physical size. See, the size of STATCOM. STATCOM has smaller footprint. STATCOM has smaller footprint. Smaller footprint means it is smaller in size. Why? Due to elimination of huge inductor and capacitor banks. It does not need large capacitor banks and large inductors. So its footprint is small. In fact, the size of because of the elimination of inductors and capacitor banks, the size of STATCOM is reduced by 30 to 40% as compared to SVC. So because of this, there is less labor cost. Less labor cost is involved in the installation of STATCOM, and STATCOM is installed in areas where cost of land is higher. So it can be installed in areas with higher land costs. Higher land cost. Because since its size is small, it will occupy less space, it will require less land. So you can use it, you can install it in those areas where cost of land is high. And it is also relocatable. It is relocatable because it has small footprint, size is small. Tomorrow, say after a few years, if it needs to be relocated to some other site, some other place, some other region, it can be very easily relocated. It can be very easily relocated. It is relocatable, whereas the SVC is not relocatable because the size of SVC is very, very large. It occupies larger land and size is very large because of large inductor and huge capacitor banks. So from physical size point of view, from the point of view of labor cost, from the point of view of the feature of being relocatable, STATCOM has an advantage over SVC. Next is response time. Response time. This is the response time. STATCOM is 1 to 2 cycles. I will write here. STATCOM is 1 to 2 cycles faster in response. Faster in response compared to 2 to 3 cycles of SVC. That means if SVC, whenever an SVC is switched in, it takes generally 2 to 3 cycles. Response time is 2 to 3 cycles. On the other hand, the STATCOM operates in 1 to 2 cycles. So therefore, STATCOM operates 1 cycle faster than SVC. Okay, it operates 1 cycle. So therefore, we can say STATCOM begins to compensate. STATCOM begins to compensate reactive power Q 1 cycle earlier. 1 cycle earlier than SVC. So therefore, the response time of STATCOM is faster, 1 cycle faster than that of SVC. So therefore, it can be used in those applications like in dynamically variable system, such as transmission lines or industrial applications operating with large random peaks, where the peaks random peaks of reactive power demand, and random peaks are coming anytime, and which require very faster operation. So this faster response can have a significant impact on effectiveness of reactive power compensation. So in those applications where the peaks of larger peaks of reactive power are there, like transmission lines and industrial systems, where the random peaks of reactive power come anytime and where faster response is required, STATCOM has an advantage. So this is another advantage of STATCOM over SVC. Okay. Next is losses. Losses are slightly higher in STATCOM than in SVC. That will be clear to you with the help of this diagram. Let me draw the diagram. This is 0, 0.5 per unit 1, 1.5, and this is again 0, 0.5, 1.0, minus 0.5, minus 1.0. This is MVA reactive in per unit, and this is MVA capacitive in per unit. That means this is inductive region of operation and this is capacitive region of operation. In the inductive region of operation, the reactive power is MVA R means reactive. In the capacitive region, the reactive power is MVA C means capacitive. Okay. And these are power losses. This x-axis is reactive power, y-axis is losses. So the losses vary like this. Let me show you. These are interface magnetics loss. Let me first of all write, then I will explain. Interface magnetics loss. Okay. Next loss is transformer loss. This is, you have a coupling transformer in STATCOM also, which is because your STATCOM is generally coupled to the transmission line through a coupling transformer. So this shows transmission loss, transformer loss. Okay. Then you have converter loss. This is converter loss. And total losses are sum of all these losses. This is total losses, which is equal to magnetics loss plus converter loss plus transformer loss. These are the total losses. Just like whether your shunt compensator is a STATCOM or SVC, at zero reactive power compensation, the losses are minimum. But as the reactive power compensation increases in the inductive range or in the capacitive range, both in case of SVC as well as in case of STATCOM, the losses linearly increase, you can see. But the losses are slightly more in STATCOM than in SVC. This curve shows the losses in the interface magnetics, because the STATCOM is coupled with the transmission line through some interface magnetics. There are small interface inductances are there, and these show those inductance losses. Inductance losses are minimum here, and then as the reactive power compensation increases, more current flows through the inductor, interface inductor, and losses increase, whether your STATCOM is operating in inductive region or in capacitive region. Similarly, so all the reactive power exchange with the system takes place through the transformer, coupling transformer. So coupling transformer losses are again minimum at near the zero reactive power compensation, and as the reactive power compensation in either direction increases, the transformer losses also increase. The most significant losses in STATCOM are converter losses, because they were STATCOM converter is basically a PWM voltage source inverter. It operates at a very high switching frequency of the order of maybe 5 kilohertz or 10 kilohertz or more than 10 kilohertz. So switching power losses are significant in converter switches, and there are conduction losses also. So therefore the power losses, converter switch losses are higher, or converter losses are higher than other losses. And converter losses increase as reactive power compensation increases, and then the total losses are sum of all these losses, and these are the total losses. So therefore, the power losses are slightly higher in STATCOM than in SVC. However, in future, there is a silver lining, because as there is more and more progress taking place in the switches, power semiconducting devices, in future we will have switches with lower losses. Okay, so therefore these switching power losses or switch losses, converter losses, can be in future, maybe after 4 or 5 years, they will come down, and therefore overall losses will also come down, and these overall losses will become less than SVC losses. On the other hand, the losses in SVC are not going to get affected even after 30 years, 40 years, because in SVC the main losses are in thyristor switches, and not in thyristor switches, of course. Main losses are in inductor banks and capacitors, and the inductor losses are not going to change in future also. So therefore, assuming that the SVC losses will remain same down the line, say after 10 years or 15 years, but after 10 to 15 years, the converter losses of STATCOM will tremendously come down. So overall or total losses of STATCOM will be less than, in future will be less than the SVC losses. However, this time this goes in favor of SVC. Presently SVC has slightly less losses than STATCOM, but in future, 5 to 10 years down the line, STATCOM will have less losses than SVC, and therefore you will start replacing all these SVCs at all those locations where they are installed by STATCOMs. Okay, so this is about losses. And then installation cost. Next is installation cost. This is G. Installation cost is 120% to 150% of cost of SVC installation. The installation cost of STATCOM is higher. It is 120% to 150% of the installation cost of SVC. So therefore, this point also goes in favor of SVC. However, in future, as the technology progresses, the cost of STATCOM installation will fall. It will come down, and in most of the applications, STATCOM technology will start replacing SVC technology. So these are various points of comparison between STATCOM and SVC. About 6 to 7 points of comparison we have discussed. The first point of comparison was VI and VQ characteristics, and that goes in favor of STATCOM, because in case of STATCOM has the ability of maintaining the current constant independent of the voltage. So reactive power is directly proportional to bus voltage, whereas in SVC current linearly decreases or varies with voltage, so that reactive power varies as square of the voltage. So STATCOM provides better or more effective compensation than SVC, so that for same level of compensation, the cost of STATCOM will be less than cost of SVC, or cost of SVC will be more than cost of STATCOM. So this point goes in favor of STATCOM. Second is transient stability improvement. Because STATCOM has the ability of maintaining the current constant, and it provides more effective compensation, the transient stability improvement provided by STATCOM is better than that of SVC, so that for same transient stability improvement, the cost of STATCOM or the rating of STATCOM is less than that of SVC. So this also goes in favor of SVC. In favor of STATCOM. Third is capability to exchange real power. In addition to exchange of reactive power, STATCOM has the capability to exchange real power also. And this feature is not there with SVC. So this point also goes in favor of STATCOM. Fourth is physical size. The physical size is smaller. Physical size of SVC is smaller due to the elimination of huge inductor and capacitor banks. It is reduced by 30 to 40%. Size, I mean, is reduced by 30 to 40%, which involves less labor cost, less land required. So it can be used in those areas where where the cost of land is high, and STATCOM is relocatable also because of its smaller size. Next is response time. The response time of STATCOM is one cycle faster than that of SVC. So therefore, in those applications where very fast response is required, STATCOM has a preference over SVC. Next is losses. The losses are slightly higher in STATCOM than SVC. So this point goes in favor of SVC. But in future, I told you that as the technology progresses, as there are more progresses in the power semiconducting devices, the converter costs will come down, and the cost of STATCOM in future, maybe after 5 or 10 years, STATCOM will have less losses than SVC. But presently, STATCOM has slightly more losses than SVC. And then installation cost. Installation cost of STATCOM is 120 to 150% of that of SVC, so it is higher. So this point also goes in favor of SVC. But again, I told you that in future, as technology progresses, cost of STATCOM installation will fall. And in most of the application, you will see that STATCOM technology will replace SVC technology. So this is about the comparison between STATCOM and SVC. So therefore, where cost is the main factor, like poor states in India, which cannot afford large costs of STATCOM, because presently the cost of STATCOM is higher than cost of SVC. So if you have to make a choice between the two, if cost is the consideration, then you will definitely go in favor of SVC. But if other features are consideration, like cost is not consideration, response time is the consideration, effectiveness of compensation is the consideration, transient stability improvement is the consideration, and response time is the consideration, then you will definitely go in favor of STATCOM. Okay, so therefore presently you will see that at many places in India SVCs are installed, and at some places STATCOMs are installed. I will share with you some diagrams of STATCOM. This is a STATCOM substation which is installed somewhere in the world. I don't know where is this location. So you can see STATCOM is not a small thing. Its substation is very, very large. These are transformers. This is the converter. This is the converter you can see. Okay. Some more these pictures I'm going to share with you. And this is the capacitor bank of shunt capacitors in SVC. You can see these are all capacitor banks. You can see capacitor banks are very heavy in case of SVC, and this makes SVC very bulky as compared to STATCOM. In case of STATCOM, these are not needed. These capacitor banks are not needed. Okay. Another picture I'm going to share with you. This is another picture of a STATCOM. Okay, it's installed in France, somewhere in France. Okay, and this is the diagram or picture of one phase of STATCOM converter. It's a huge converter. Converter is not small because the reactive power exchange is very, very large. Okay, this is single converter valve unit in a STATCOM. Single converter valve. Okay, and STATCOM comprises of large number of such valves. And this is a very interesting picture I'm going to share with you. You can see it is written here, the small size of STATCOMs allows them to be constructed at the manufacturing plant, then shipped to the required location. The above picture shows a STATCOM being loaded in a heavy cargo aircraft. You can see it can be loaded in a cargo area. That means it can be relocated. For example, you don't need it here. You need it somewhere else. You just load it in a cargo aircraft and relocate it. On the other hand, it is not possible to relocate an SVC because of large footprint or larger size of SVC. So that completes our discussions on SVC, shunt compensators like SVC and STATCOM, the comparative analysis of the two. So that's all about the shunt compensators. And I advise all of you to revise, to go through these lectures and, draw a comparison between the two and see which is better. Study the characteristics of the two types of compensators. Watch all the lectures which I have discussed with you. So for some 5 to 6 lectures on STATCOM and SVC. And in future, From next lecture onwards, we are going to start our discussions on series compensators. Okay, our discussions on shunt compensators are over. We have discussed in greater details, the two shunt compensators, SVC and STATCOM, and we have drawn a comparison between the two. So from next lecture onwards, hopefully I will start my discussions on series compensators. Thank you very much.